All right, everyone. In this video, we're going to determine number of signals and exercise that. When you're determining number of signals, we of course want to look at the overall structure and see if there's any symmetry present. For example, if you were to look at this molecule that I'm going to draw in here, there would be a symmetry across the structure. I'd have 1, 2, 2, 3, 3, and 4. Because of that line of symmetry down the middle, we have equivalents across that line of symmetry. So we always want to detect that symmetry right off the bat. If the structure is overall not symmetrical, just start at one side and count to the other. For example, on the far left, we have 1, 2, 3, 4 for the CH, don't forget that one there. And then the methyl groups are coming off the same carbon, so they will both be equivalent to one another. 5 signals. In the next structure, I'm going to start on the far left side, no overall symmetry. We have 1, 2, 3, 3, 4, 5, 6, and 7. 7 signals for the middle molecule. Looking at the far right, there's no overarching symmetry, but there's going to be symmetry across the benzene ring. So I might start there. 1, 2, 2, 3, 3, because the line of symmetry, 4, 5, and 6. 6 total signals. Looking at the bottom right molecule, I'll acknowledge that there's no overall symmetry on the ring. So I have 1, 2, 3, 4, 5. I have to count all of those differently on the ring because of the lack of symmetry. 6, 7, 8, and 9. 9 signals. Now, where we really have to slow down and be meticulous is when we're on a cycloalkane ring that's substituted. Okay, on the exam, they might just give you the structure like this. And if they haven't drawn in all the hydrogens, you would want to draw in all the hydrogens with perspective wedges because the cis and trans relationships may matter. I've already done that for us. Let's acknowledge that there's a line of symmetry here, and similarly in the right structure, there's a line of symmetry. Note that the bromines here are cis to one another. If I'm starting, say, with these two hydrogens, I would say that they're diastereotopic. They're on the same carbon, but the one in the solid is seeing both of the bromines trans, the one in the dash is seeing them both cis, so they're non-equivalent. I count them separately. I'm then going to have 3 and 3, both on a carbon with a bromine, and they see a bromine across in a trans fashion. And if I just look at these two hydrogens here, they have the same constitution, but they're going to see the bromine closest to it differently from a cis-trans standpoint, so I'll count those differently. And then because of that line of symmetry, I'm going to count this one as 4 and this one as 5, meaning the ones that I counted as 4 are each seeing the bromine closest to them in a trans fashion, and the ones that I counted as 5 respectively are both seeing the bromine closest to them, cis. In other words, if you've got cis bromines or cis substituents, then across that line of symmetry, it's going to be cis hydrogens that would be equivalent to one another. Now let's check out if we had trans substituents. Starting with these two hydrogens, these are now going to be equivalent because they're each seeing a bromine cis and a bromine trans, and they're equidistant to the bromines. I'm then going to have 2 and 2, they're each on a carbon with a bromine, and then across the ring respectively, they would see a bromine cis. If I count these two hydrogens, they would be different, 3 and 4. They have the same constitution, but they're seeing the bromine closest to them in a trans fashion versus a cis fashion. Then because of the trans substitution of the ring, I'm going to count 3 and 4. Notice how we have 3 protons, one on the solid, one on the dash, respectively, though. This one is seeing the bromine closest to a trans, and so is that hydrogen there, hence why they're equivalent. Or I could say the one on the dash here that I've labeled 4 is seeing the bromine cis. The one that I've labeled 4 is also seeing the bromine cis there. So to kind of summarize what I'm kind of getting at is if the ring is substituted in a trans fashion, then across that line of symmetry, it's likely going to be the case that trans protons are equivalent to one another. But if we've got cis substitution to the ring, then across that line of symmetry, cis protons will be equivalent to one another. So we definitely want to slow down with cycloalkane rings and consider cis-trans relationships. All right, moving on to the next page here. For A, B, and C, notice I've just duplicated the structure up top with all the hydrogens drawn out. Again, if you're on a cycloalkane ring, to most accurately determine number of signals, you want to draw in all the hydrogens with their respective wedges. Starting with example A, we're going to notice that there is no overall symmetry. I repeat, no overall symmetry because we have different halogens. So starting with these two hydrogens, I'm going to say that they're 1 and 2. One is seeing the halogens in a cis fashion, the other seeing them in a trans fashion. They're diastereotopic. I'm then going to count 3 and 4 because they're each on carbons with different halogens. If I'm looking at these two, I'm going to count that as 5 and 6. They're each seeing the bromine closest to them differently. One seeing it cis, the other seeing it trans. And because of the lack of symmetry, I'm going to have to count these as 7 and 8. These are diastereotopic to one another because they see the chlorine differently from a cis-trans standpoint. So a lot of signals in that molecule. Slow down, look at the cis-trans relationships. Looking at example B, we're going to look at the top structure here. I'm going to say that the ones on the solid are both equivalent. They're each seeing the bromine cis and the chlorine trans. And then the hydrogens on the dash wedge are each seeing the chlorine cis. If I separately just evaluated those two, I know that they're going to have different signals. They're diastereotopic, one seeing the bromine cis, the other seeing it trans. Two signals in that structure. Looking at the far right molecule, we'll acknowledge that there is no overall symmetry because we have different halogens substituting the ring. Accordingly, I'm going to count 1 and 2. Those protons are on carbons with different halogens. And then if I look at these two, they're on the same carbon, yes, but they're seeing the halogens differently. The one on the solid sees them both cis. The one on the dash sees them both trans. So I'm going to count 3 and 4. 4 overall signals. Again, can't stress this enough with cycloalkane rings. We slow down and look at the cis-trans relationships, and if protons have the same constitution and the same stereochem, they will be equivalent. But if they're differing in their stereochem and have the same constitution, they're diastereotopic and should be counted differently. All right, next row, starting on the far left with example D. I see that there's no overarching symmetry, so I'll start on one side of the structure and work my way across. I've got 1, 2, 3, then I'll have 4, 5, and 6. 6 total signals. Looking at example E, no overall symmetry, but there is symmetry across the benzene ring. So I'm going to count 1, 1, 2. I'll then count 3, 3, 4, and 4 again because of the para substitution. 5, 6, and 7. 7 overall signals. Looking at example F, notice there is an overarching symmetry. We have NO2 groups on each side. Therefore, I'll have 1, 2, 2, and 3 because of that symmetry. These are both equivalent. Total of 3 signals. Going on to the next row, for example G, I am noticing that we have para substitution and we have the same substituent. So overarching symmetry. 1, 1, 1, 1, 1, 1. All those methyl groups are equivalent. Then I'll have 2, 2, 2, and 2. Again, this is because there's that overarching symmetry. Comparing that to example H, notice how we have the terp-butyl group on this side, but then we have an O and then the terp-butyl group, so no overarching symmetry, but there will be symmetry across the ring in the para fashion. I'm going to count 1, 1, 1, then 2 and 2, 3 and 3. Again, that's because the ring is para substituted. And then 4, 4, 4. Those methyl groups will all be equivalent there. So definitely take a second to look at that comparison. All right. And finally, looking at this ring here, there is an overarching symmetry in this direction and in this direction. And because of that, we'll have 1, 1, 1, 1, 2, 2, 2, and 2. Total of 2 signals. Now, for just being comprehensive and showing you another example, let's say that the ring were substituted like this, such that there's only symmetry in this direction, but not in that direction. As drawn, there would be 1, 1, 2, 2, 3, 3, and 4 signals total. Okay, but if that's 2 benzene rings with no substituents, we had a symmetry in this direction and in this direction. Okay. So notice that we kind of used our strategy of, is it homotopic and antiotopic, diastereotopic, non-equivalent? We kind of had to use that 4-ring structures for cycloalkanes. Again, can't emphasize this enough. Slow down for those rings, determining if protons are equivalent or non-equivalent by seeing if they have the same constitution and stereochem. These here had the same constitution, but they saw the halogen differently, trans versus cis, so we had to count them separately. If there's no overarching symmetry, we start on one side and work our way to the other. And just be sure to track that even if there's no overarching symmetry, sometimes there's symmetry across a ring if it's, say, para-substituted. Or if you're on a ring and you have the same substituent on either side, then that's where we could also have symmetry and equivalence across that line of symmetry. All right. Now, if you struggled with any of those examples, please go back and watch the video again, work it out. Gotta be able to count number of signals. And if it helps to draw out the hydrogens, at a given position, for example, like with this structure here, drawing out CH3, H, and H, by all means, you can draw out the hydrogens. I just recommend that for time's sake, you get in the habit of not having to draw them out, just to be faster. But where I would definitely draw them out is on a substituted cycloalkane ring, for sure. And if you struggle with detecting them on the benzene ring, for whatever reason, you can also draw out the hydrogens on the benzene ring as well.